October 25, 1944, 1,347 hours. USS Yorktown, Philippine Sea. What Japanese kamikaze pilots feared more than death itself was the distinctive four-barreled roar of American 40mm Bofors anti-aircraft guns that could tear their aircraft apart at ranges exceeding 4,000 yards, with a mechanical precision that transformed their sacred mission into systematic destruction. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. Petty Officer First Class William Bull Mackenzie gripped the elevation handwheel of Mount Baker 7, tracking a Mitsubishi A6M0 through the crystalline Pacific sky as it descended in what American naval intelligence had recently classified as a special attack approach. The aircraft bore the distinctive red Hinamaru markings of the Imperial Japanese Navy, but something about its flight pattern indicated this pilot had no intention of returning to his carrier. Mackenzie had been operating Bofors anti-aircraft systems for 18 months, since the installation program had transformed American naval defense capabilities in the aftermath of devastating losses at Pearl Harbor. His gun mount represented the culmination of Swedish engineering excellence adapted to American manufacturing capacity, creating a weapon system that had fundamentally altered the mathematical equations governing aerial warfare in the Pacific theater. The approaching Zero maintained a steady descent angle that violated every principle of tactical aviation Mackenzie had observed during his combat service. Conventional attack patterns involved high-speed approaches with evasive maneuvering designed to minimize exposure to defensive fire. This aircraft flew straight and level, as though the pilot had prioritized target acquisition over personal survival in ways that seemed to defy rational military doctrine. Mackenzie adjusted his aim point to compensate for the aircraft's predictable flight path, while his loader, Seaman James Patterson, verified the ammunition feed mechanism that would deliver high-explosive shells at a rate of 120 rounds per minute. The Bofors system had been designed to engage multiple targets simultaneously through coordinated fire patterns that created overlapping zones of destruction no aircraft could penetrate without sustaining catastrophic damage. What Mackenzie could not have known was that the approaching pilot, Flight Petty Officer Hiroshi Tanaka, had spent the previous evening writing farewell letters to his family, while consuming ceremonial sake with 19 other volunteers who had accepted assignment to the newly formed Shimpu Special Attack Unit. Tanaka carried photographs of Emperor Hirohito, poems composed for his parents, and explicit instructions to guide his aircraft directly into the Yorktown's flight deck, in a final act of devotion to imperial military objectives. But Tanaka also carried something else that his commanding officers had not anticipated: intimate knowledge of American anti-aircraft capabilities gained through 18 months of aerial combat against increasingly sophisticated defensive systems. He had witnessed dozens of experienced pilots destroyed by weapons that seemed to anticipate their movements with supernatural accuracy, creating barriers of explosive steel that rendered conventional attack approaches virtually impossible. The Bofors guns represented the most formidable component of this defensive network, combining rapid-fire capability with precision that exceeded anything Japanese military planners had encountered during their initial Pacific operations. Unlike the lighter 20mm cannons that required direct hits for effective destruction, or the heavier 5-inch guns that fired time-delayed shells with limited accuracy against maneuvering targets, the 40mm Bofors system delivered proximity-fused projectiles that detonated within lethal radius of approaching aircraft. Tanaka understood that his survival during the final approach phase depended entirely on avoiding the engagement envelope of these weapons, which extended from 400-500 yards maximum range down to 500 yards minimum effective distance. The mathematical challenge seemed impossible, maintaining sufficient altitude and distance to avoid defensive fire, while achieving the precision necessary for successful impact against a maneuvering target. Mackenzie commenced firing at 800 yards, well within the optimal engagement parameters for his mount. The 4 barrels of the Bofors system discharged in sequence, creating a rhythmic thunder that had become known throughout the Pacific Fleet as the sound of salvation. Each shell weighed 2 pounds and contained explosive charges designed to fragment into hundreds of steel projectiles upon detonation, creating lethal zones that extended 75 feet in all directions from the point of explosion. The first shells bracketed Tanaka's aircraft at ranges that would have guaranteed destruction against any target maintaining predictable flight characteristics. But the Kamikaze pilot had anticipated this engagement pattern and implemented evasive maneuvers specifically designed to defeat Bofors' fire control solutions. He rolled his Zero into a spiraling descent that constantly changed his aspect angle and relative velocity, forcing Mackenzie to continuously adjust his aim point while compensating for rapidly shifting target parameters. The engagement lasted 43 seconds and involved the expenditure of 127 rounds of 40mm ammunition from Mackenzie's mount alone. Additional Bofors positions throughout the task force contributed coordinated fires that created overlapping fields of destruction through which no conventional aircraft could have survived. The combined firepower, represented by 12 quad-mounted Bofors systems, exceeded the anti-aircraft capability of entire land-based installations, concentrated within the defensive perimeter of a single naval task force. Tanaka's Zero disintegrated 200 yards from Yorktown's starboard beam, transformed from aircraft into burning fragments by proximity fuzzed shells that had detected his presence and detonated with timing precision measured in milliseconds. The pilot's final transmission, monitored by American communication intercept stations, consisted of a single word repeated 3 times: Bakemono, monster. Mackenzie watched the burning wreckage spiral into the Pacific, while his gun crew prepared for the next engagement, unaware that they had just participated in a tactical evolution that would fundamentally transform Japanese military strategy for the remainder of the Pacific War. The systematic destruction of kamikaze aircraft by American anti-aircraft systems had begun to create psychological effects within Imperial naval aviation units that threatened to undermine the entire special attack program. The mathematical reality was becoming undeniable. American defensive capabilities had evolved to the point where even pilots willing to sacrifice their lives could not achieve reliable success against properly equipped naval formations. The Bofors anti-aircraft system represented the technological answer to fanatical determination, proving that superior engineering could defeat spiritual commitment regardless of the personal sacrifices enemy personnel were prepared to make. The development of effective anti-aircraft defense had become an existential requirement for American naval operations, following the catastrophic losses sustained during the initial phases of Pacific combat. Japanese aviation units had demonstrated tactical superiority during the Pearl Harbor attack and subsequent operations through combination of advanced aircraft design, superior pilot training, and innovative tactical approaches that overwhelmed existing American defensive capabilities. The Zero fighter represented the pinnacle of Japanese aeronautical engineering, combining exceptional maneuverability with extended range capabilities that enabled operations far from base installations. Japanese pilot training programs had produced aviators whose skill levels exceeded American standards through intensive preparation that emphasized precision flying and aggressive tactical approaches. Combined with surprise attack strategies that exploited American defensive vulnerabilities, these advantages had enabled Japanese forces to achieve air superiority throughout the Western Pacific during 1942. American naval commanders recognized that technological solutions would be required to overcome these tactical disadvantages, since pilot training programs could not be accelerated sufficiently to match Japanese proficiency levels within acceptable timeframes. The solution involved systematic upgrading of anti-aircraft capabilities through installation of advanced weapon systems that could achieve defensive effectiveness regardless of individual crew experience or training levels. The Bofors 40mm anti-aircraft gun had been selected for this role based on combat performance evaluations conducted by Allied naval forces operating in European waters. Swedish engineers had designed the system to combine rapid-fire capability with accuracy levels that enabled effective engagement of high-performance aircraft under combat conditions. The weapon fired shells at muzzle velocities exceeding 800 feet per second, with sufficient accuracy to achieve lethal hit probability against maneuvering targets at ranges up to 400–500 yards. More significantly, the Bofors system had been engineered for operation by crews with minimal specialized training, using automated loading mechanisms and simplified fire control procedures that enabled rapid deployment aboard naval vessels. American manufacturing facilities had adapted the Swedish design for mass production, using industrial techniques that could deliver completed weapon systems within months rather than years required for alternative solutions. The installation program had commenced during late 1942 and achieved full deployment throughout the Pacific Fleet by mid-1944, transforming American naval air defense from liability into decisive advantage. Each major combatant vessel received multiple Bofors mounts positioned to provide overlapping fields of fire that created impenetrable barriers against approaching aircraft. The combined firepower represented by these installations exceeded anything Japanese military planners had anticipated when formulating their strategic approaches. The psychological impact on Japanese aviation personnel had become apparent through intelligence reports that documented declining morale and increasing reluctance to engage American naval formations. Pilots who had previously demonstrated exceptional courage and tactical skill were reporting equipment malfunctions and weather delays that prevented completion of assigned missions. Squadron commanders noted increasing instances of aborted attacks and premature withdrawal from engagement areas. Most significantly, captured Japanese documents revealed that Imperial Naval Aviation leadership had begun modifying tactical doctrines to acknowledge American anti-aircraft superiority. New operational procedures emphasized night attacks, low-altitude approaches, and poor weather operations designed to minimize exposure to defensive fires. These modifications represented acknowledgement that conventional daylight attacks against properly equipped American formations had become tactically impossible. The introduction of kamikaze tactics during October 1944 represented Japanese recognition that traditional aviation approaches could no longer achieve acceptable success rates against evolved American defensive capabilities. If experienced pilots using advanced aircraft and proven tactical methods could not penetrate American air defenses, perhaps inexperienced pilots using obsolete aircraft in suicide attacks might achieve better results through elimination of self-preservation considerations that constrained conventional operations. The mathematical logic appeared sound. Pilots who ignored defensive fire during final attack phases could potentially achieve impact success, despite sustaining damage that would force conventional attackers to abort their missions. Kamikaze operations eliminated the requirement for pilot survival, theoretically enabling continued attacks until target destruction, regardless of defensive fire effectiveness. But this logic failed to account for the mechanical precision of proximity-fused anti-aircraft shells that could destroy aircraft regardless of pilot determination or willingness to sustain damage. The Bofors system did not rely on pilot psychology or self-preservation instincts to achieve defensive success. It simply delivered explosive projectiles to precise locations in space, with timing accuracy that rendered evasive action impossible within lethal radius parameters. Japanese kamikaze operations had encountered an opponent that could not be intimidated, demoralized, or overcome through spiritual determination. The 40mm Bofors anti-aircraft gun represented pure mechanical function, optimized for aircraft destruction, immune to psychological warfare, and indifferent to enemy sacrifice or commitment levels. The Bofors 40mm anti-aircraft system represented a revolutionary advancement in defensive technology that fundamentally altered the tactical balance between attacking aircraft and defending vessels. The weapon combined rapid-fire capability with accuracy levels that had been impossible to achieve using previous-generation anti-aircraft systems, creating defensive zones that approaching aircraft could not penetrate without sustaining catastrophic damage. The basic system consisted of 4 40mm cannons mounted on a single platform with integrated fire control equipment that enabled coordinated engagement of multiple targets. Each cannon fired shells at rates up to 120 rounds per minute, creating combined firepower equivalent to 480 projectiles per minute from a single mount. Multiple mounts installed aboard individual vessels provided overlapping fields of fire that eliminated gaps in defensive coverage. The ammunition represented equally significant technological advancement. Each 40mm shell contained proximity-fuzzed warheads that detonated automatically when sensors detected aircraft presence within lethal radius parameters. This eliminated the requirement for direct hits that had limited effectiveness of previous anti-aircraft systems, since proximity detonation created fragmentation patterns that could destroy aircraft through near-miss explosions. The fire control system integrated radar detection with mechanical computing devices that calculated target trajectory and optimal aim points for successful interception. Operators could engage targets at maximum detection range and maintain accurate fire throughout the approach phase, creating sustained defensive barriers that aircraft could not cross without encountering multiple proximity explosions. The mounting system enabled rapid traverse and elevation changes that allowed engagement of aircraft approaching from any direction at altitudes from sea level to 25,000 feet. The combined flexibility meant that individual Bofors mounts could engage multiple targets in sequence, or coordinate with other mounts to concentrate firepower against single high-priority threats. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. Installation procedures had been standardized to enable rapid deployment aboard vessels of all types, from destroyers to aircraft carriers. The modular design allowed adaptation to existing ship configurations without requiring extensive structural modifications, enabling fleet-wide implementation within compressed timeframes that matched operational requirements. The crew training program emphasized mechanical procedures rather than individual marksmanship skills, enabling rapid preparation of operators who could achieve effective results regardless of previous military experience. The automated loading mechanisms and simplified fire control procedures reduced the specialized knowledge required for successful operation while maintaining accuracy levels that exceeded manually operated systems. Maintenance requirements had been minimized through robust engineering that enabled sustained operation under combat conditions with limited technical support. The weapon systems could function effectively despite battle damage, environmental exposure, and intensive use patterns that would disable more complex equipment. This reliability proved essential during extended combat operations where technical support was unavailable. The ammunition supply system enabled sustained engagement capabilities that exceeded aircraft endurance parameters. Each Bofors mount could maintain continuous fire for periods exceeding the flight time of approaching aircraft, eliminating tactical advantages that attackers had previously gained through ammunition conservation requirements that limited defensive fire duration. The integration with shipboard power and communication systems enabled coordinated defensive operations that transformed individual vessels into components of larger defensive networks. Information sharing between platforms allowed optimal target assignment and ammunition conservation, while maintaining defensive coverage that prevented successful penetration by attacking formations. The cost-effectiveness analysis demonstrated that Bofors installations provided defensive capability that exceeded the value of potential losses from successful enemy attacks. The investment in advanced anti-aircraft systems generated returns through reduced battle damage and personnel casualties that justified the procurement and installation expenses. Most significantly, the psychological impact on enemy aviation personnel created strategic advantages that extended beyond direct combat effectiveness. Knowledge that American vessels possessed impenetrable air defenses influenced Japanese tactical planning and operational decision-making in ways that reduced the overall effectiveness of Imperial naval aviation throughout the Pacific theater. The Bofors 40mm anti-aircraft system had transformed American naval vessels from vulnerable targets into floating fortresses capable of defeating sustained aerial attacks regardless of enemy determination or tactical innovation. The mathematical equations governing air-sea combat had been fundamentally altered in favor of defensive forces equipped with technology that could defeat attacking aircraft through mechanical precision rather than human courage or tactical skill. Japanese kamikaze operations represented the final attempt to overcome these technological advantages through spiritual determination and willingness to accept unlimited casualties. The collision between fanatical commitment and mechanical precision would determine whether human dedication could triumph over engineering excellence, or whether superior technology would prove immune to psychological warfare and sacrificial tactics. The thunder of Bofors guns echoing across Pacific battlefields provided the answer to this fundamental question about the relationship between technology and human will in modern warfare. Lieutenant Commander Yukio Sato stood before the weathered wooden table that served as his squadron briefing platform, studying the faces of 17 pilots who had volunteered for what Imperial Naval Command euphemistically termed special attack operations. The morning air carried the scent of aviation fuel and tropical vegetation, but beneath these familiar odors lingered something else that Sato had only recently learned to identify, the distinct smell of fear masquerading as determination. Each pilot before him had written farewell letters to their families during the previous evening. Each had consumed ceremonial sake, while reciting poems dedicated to Emperor Hirohito. Each had accepted assignment to missions that offered no possibility of return, embracing death as the ultimate expression of loyalty to imperial military objectives. Yet Sato observed something in their expressions that challenged every assumption about spiritual preparation overcoming physical limitations. The reports from yesterday's operations had fundamentally altered the psychological landscape surrounding kamikaze tactics. Of 23 aircraft launched against American naval formations near Leyte Gulf, only 3 had achieved successful target contact. The remaining 20 aircraft had been systematically destroyed by defensive fire at ranges that prevented completion of their sacred missions. Most disturbing were the radio transmissions monitored during the final moments of these engagements, revealing psychological breakdown among pilots who had expected glorious sacrifice but encountered technological annihilation instead. Flight Petty Officer Kenji Nakamura, one of only 2 pilots to return from yesterday's mission due to mechanical difficulties that forced early return, had provided detailed debriefing that documented American anti-aircraft capabilities exceeding all previous intelligence estimates. Nakamura described defensive fire patterns that created impenetrable barriers around target vessels, transforming suicide attacks into exercises in futile destruction that achieved no strategic objectives while consuming irreplaceable aircraft and trained personnel. Most significantly, Nakamura reported that American gunners appeared to anticipate kamikaze approach patterns with supernatural accuracy, positioning defensive fires to intercept aircraft before pilots could achieve diving positions necessary for successful impact. The precision of this defensive fire suggested either advanced fire control technology or tactical intelligence that enabled American forces to predict Japanese attack methods with mathematical certainty. Sato faced an unprecedented command challenge. Imperial Naval Headquarters continued demanding kamikaze operations against American formations, despite mounting evidence that these missions achieved negligible strategic results, while depleting aviation resources at unsustainable rates. The psychological foundation supporting special attack operations required maintaining pilot conviction that their sacrifices would achieve meaningful military outcomes, but observable reality increasingly contradicted these essential beliefs. The mathematics were becoming undeniable. If experienced pilots using advanced aircraft could not penetrate American defensive systems, the logical conclusion suggested that kamikaze tactics represented strategic failure rather than innovative solution to conventional tactical limitations. Yet questioning the effectiveness of special attack operations bordered on treason against imperial military doctrine that demanded absolute faith in spiritual superiority over material disadvantage. Sato had observed gradual changes in pilot behavior that indicated growing awareness of these tactical realities, despite official prohibition against discussing mission effectiveness. Volunteers for kamikaze operations increasingly demonstrated reluctance that manifested through equipment complaints, weather concerns, and medical issues that delayed mission execution. Experienced pilots requested assignment to conventional operations that offered survival possibilities rather than certain death, in pursuit of questionable strategic objectives. Most troubling was the emergence of what medical personnel described as combat fatigue symptoms among pilots who had not yet participated in combat operations. Fear of impending kamikaze missions created psychological stress that impaired flying performance and decision-making capabilities essential for successful mission completion. The irony was becoming apparent. Pilots needed exceptional skill and determination to overcome American defensive capabilities, but knowledge of these capabilities undermined the psychological foundation necessary for developing exceptional performance. The briefing material Sato had received from Naval Intelligence contained disturbing analysis of American anti-aircraft weapon systems that explained the systematic destruction of Japanese aircraft during recent operations. The 40mm Bofors guns represented technological advancement that fundamentally altered the tactical equations governing air-sea combat in ways that Japanese military planners had failed to anticipate during strategic planning phases. These weapons combined rapid-fire capability with accuracy levels that enabled effective engagement of high-performance aircraft at ranges exceeding 4,000 yards. More significantly, the proximity-fused ammunition eliminated the requirement for direct hits by creating lethal fragmentation patterns that destroyed aircraft through near-miss explosions. The mathematical result was defensive coverage that approaching aircraft could not penetrate without sustaining damage sufficient to prevent mission completion. The psychological impact on Japanese aviation personnel had been immediate and profound. Pilots who had previously demonstrated exceptional courage and tactical skill reported increasing reluctance to engage American naval formations equipped with advanced defensive systems. Squadron commanders noted declining volunteer rates for kamikaze operations, despite continued emphasis on spiritual preparation and patriotic dedication. Intelligence reports indicated that American naval forces had achieved near-complete defensive effectiveness against kamikaze attacks through systematic deployment of Bofors anti-aircraft systems throughout the Pacific Fleet. The success rates that had initially justified special attack operations had declined to levels that made continued kamikaze missions strategically counterproductive while consuming irreplaceable aviation resources. Sato understood that his pilots required honest assessment of tactical realities balanced against maintenance of combat effectiveness necessary for mission success. Acknowledging American defensive superiority might undermine psychological preparation essential for kamikaze operations, but failing to prepare pilots for actual combat conditions would guarantee mission failure while achieving no strategic objectives. The solution required developing modified tactical approaches that could overcome specific limitations of American defensive systems while maintaining the essential elements of special attack doctrine. This meant identifying vulnerabilities in Bofors anti-aircraft coverage that could be exploited through innovative attack methods that preserved mission effectiveness while acknowledging technological realities. Intelligence analysis suggested several potential approaches that might achieve greater success rates against American formations. Night operations could reduce defensive fire accuracy by limiting visual target acquisition and fire control effectiveness. Low-altitude approaches might exploit radar limitations while minimizing exposure time within Bofors engagement envelopes. Coordinated multi-directional attacks could overwhelm defensive fire distribution while ensuring some aircraft achieved successful target contact. Each approach required fundamental modifications to existing kamikaze doctrine, while maintaining spiritual elements essential for pilot motivation and mission commitment. The challenge involved adapting special attack operations to technological realities, without acknowledging that these adaptations represented admission of tactical failure in original kamikaze concepts. Sato began his briefing by addressing the elephant that dominated every pilot's private thoughts, while remaining officially unmentionable within imperial military contexts. The American defensive capabilities that had destroyed 20 of 23 aircraft during yesterday's operations represented technological challenges that required tactical responses rather than spiritual solutions. The enemy has developed anti-aircraft systems that exceed previous intelligence estimates, Sato announced, choosing his words carefully to avoid implications that might be interpreted as defeatist. These systems require modified approach techniques that will enable successful completion of your sacred missions despite American technological advantages. The relief visible on pilot faces confirmed Sato's assessment that acknowledgement of tactical realities would enhance rather than undermine mission effectiveness. Pilots who understood specific challenges they would encounter could develop appropriate responses rather than relying on spiritual preparation alone to overcome technological obstacles. The Bofors anti-aircraft guns that destroyed our comrades yesterday operate most effectively against aircraft maintaining predictable flight patterns at altitudes between 1,000 and 8,000 feet. Sato continued, referencing intelligence reports that provided detailed analysis of American defensive capabilities. Modified approach techniques can exploit limitations in these systems while preserving the essential elements of special attack operations. The tactical modifications Sato outlined required exceptional flying skill combined with precise timing that would challenge even experienced pilots under optimal conditions. Night approaches demanded navigation accuracy that exceeded normal training standards while maintaining formation integrity essential for coordinated attacks. Low-altitude operations required terrain-following techniques that increased fuel consumption while reducing available approach options. Most significantly, these modifications required pilots to survive defensive fire during extended approach phases, rather than accepting immediate destruction as an inevitable component of kamikaze missions. This fundamental change in tactical philosophy challenged basic assumptions about special attack operations, while potentially improving mission effectiveness through enhanced pilot survival during critical engagement phases. The psychological transformation required for implementing these modifications represented revolutionary change in kamikaze doctrine that prioritized mission success over demonstration of spiritual devotion through willing acceptance of immediate death. Pilots would need to focus on tactical performance rather than psychological preparation for martyrdom, developing professional competence rather than spiritual acceptance of inevitable destruction. This approach offered potential solutions to the tactical challenges that had rendered conventional kamikaze operations ineffective against American defensive systems. By acknowledging technological realities and developing appropriate tactical responses, Japanese aviation forces might achieve strategic objectives that justified continued special attack operations despite mounting personnel and equipment losses. The fundamental question remained whether Japanese military leadership would accept tactical modifications that challenged basic philosophical assumptions about spiritual superiority over material disadvantage. The success or failure of these adapted kamikaze operations would determine whether imperial forces could develop effective responses to American technological advantages, or whether continued adherence to original special attack doctrine would result in complete destruction of Japanese aviation capabilities. Sato concluded his briefing with emphasis on professional execution rather than spiritual preparation, marking a fundamental shift in kamikaze doctrine that prioritized tactical effectiveness over demonstration of absolute devotion. The pilots who would implement these modifications carried responsibility for determining whether human adaptability could overcome technological superiority through intelligent application of modified tactical approaches. The morning sun rising over Mabalacat airfield illuminated faces that reflected newfound determination based on understanding rather than blind faith. These pilots would test whether acknowledgement of enemy capabilities could enhance mission effectiveness, rather than undermining the psychological foundation essential for special attack operations. The thunder of distant Bofors guns had forced evolution in Japanese tactical thinking that might preserve both pilot lives and mission objectives through intelligent adaptation to technological realities that could no longer be ignored or overcome through spiritual determination alone. Chief Gunner's mate Thomas Iron Mike Sullivan ran his calloused fingers along the pristine barrel assembly of Mount Charlie 4, conducting the pre-dawn inspection that had become his ritual during 18 months of Pacific combat operations. The 40mm Bofors gun represented the culmination of his 22-year naval career, transforming him from a sailor who maintained equipment into an artist who orchestrated mechanical precision that could determine the survival of 3,000 shipmates. Sullivan had enlisted in the Navy during 1922, when anti-aircraft defense consisted of manually operated machine guns that required individual marksmanship skills to achieve marginal effectiveness against aerial targets. His career had spanned the technological revolution that transformed naval warfare from contests between individual combatants into systematic applications of engineering excellence that enabled smaller crews to achieve capabilities that would have been impossible using traditional methods. The Bofors system embodied everything Sullivan had learned about the relationship between human expertise and mechanical precision during 2 decades of naval service. The weapon demanded technical knowledge, mechanical intuition, and leadership capabilities that extended far beyond simple equipment operation. Successful gun crews represented partnerships between human intelligence and technological capability that could achieve performance levels that neither component could accomplish independently. Sullivan commanded a crew of 12 men who maintained and operated 4 separate Bofors mounts positioned throughout intrepid superstructure. Each mount required specialized knowledge of hydraulic systems, electrical circuits, ammunition handling procedures, and fire control mechanisms that involved hundreds of individual components working in precise coordination. The complexity demanded expertise that traditional naval training programs had never attempted to develop within compressed wartime schedules. The challenge had forced Sullivan to develop innovative training methods that could transform civilian volunteers into competent anti-aircraft specialists within timeframes that conventional military education would have considered impossible. His approach emphasized understanding principles rather than memorizing procedures, enabling crew members to diagnose problems and implement solutions under combat conditions that prevented reference to technical manuals or consultation with supervisory personnel. Seaman First Class Robert Martinez represented the success of these training innovations. Martinez had joined the Navy 6 months earlier with no mechanical experience beyond basic automobile maintenance, yet now served as lead mechanic for Mount Charlie 4, with expertise that exceeded many factory-trained technicians. His transformation from complete novice to essential crew member demonstrated the potential that could be unlocked when individual motivation combined with systematic instruction and hands-on experience. The key insight that Sullivan had developed through years of equipment training was that mechanical systems responded to understanding rather than memorization. Personnel who comprehended the engineering principles underlying equipment operation could adapt to unexpected situations and implement creative solutions when standard procedures proved inadequate. This approach had enabled his crews to maintain operational readiness despite battle damage, equipment failures, and supply shortages that would have disabled conventionally trained units. Martinez embodied this principle through his ability to diagnose hydraulic pressure problems by listening to pump operations, identify electrical faults through systematic voltage testing, and implement field repairs using improvised materials when standard replacement parts were unavailable. His expertise had developed through combination of theoretical instruction and practical application that compressed years of traditional learning into months of intensive hands-on experience. The morning inspection revealed the mechanical precision that made Bofors' effectiveness possible. Each of the 4 gun barrels maintained perfect alignment despite thousands of rounds fired during recent combat operations. The hydraulic systems operated with smooth consistency that enabled rapid traverse and elevation changes essential for tracking high-speed aircraft. The ammunition feed mechanisms functioned with clockwork reliability that prevented jamming during sustained fire sequences. This mechanical excellence reflected manufacturing standards that American industrial capacity had achieved through systematic application of precision engineering principles to mass production requirements. Swedish engineers had designed the Bofors system for optimal performance, but American manufacturers had adapted these designs for production volumes that could equip entire naval fleets within timeframes that matched operational requirements. The ammunition represented equally impressive technological achievement. Each 40mm shell contained proximity-fused warheads that incorporated miniaturized electronic components manufactured to tolerances measured in thousandths of inches. The production process involved coordination between multiple industrial facilities that produced specialized components requiring different manufacturing techniques, all integrated through quality control procedures that ensured consistent performance under combat conditions. Sullivan understood that his crew's effectiveness depended on maintaining this mechanical precision, despite environmental stresses that would destroy conventional equipment. Salt air corroded metal surfaces, vibration loosened mechanical connections, and temperature variations affected hydraulic fluid properties. Preventing degradation required maintenance procedures that addressed these challenges through systematic application of protective measures and preventive replacement of components before failure occurred. The expertise required for this maintenance had been developed through trial and error during months of combat operations that revealed failure patterns and effective countermeasures. Sullivan had documented these lessons learned in detailed maintenance logs that became training resources for other gun crews throughout the Pacific Fleet. His innovations in lubrication procedures, corrosion prevention, and component replacement schedules had been incorporated into official maintenance protocols that improved fleet-wide equipment reliability. More significantly, Sullivan had developed training methods that could transfer this expertise to replacement personnel who arrived without previous mechanical experience. The high casualty rates of Pacific combat required constant crew replacements, making knowledge transfer essential for maintaining operational effectiveness. His systematic approach to technical education enabled new crew members to achieve competency levels that preserved mount effectiveness, despite personnel turnover that would have degraded conventionally trained units. The psychological foundation of this training emphasized personal responsibility for equipment performance, rather than simple compliance with prescribed procedures. Sullivan taught his crews to view themselves as partners with their equipment, rather than operators following instructions, developing emotional investment in mechanical performance that motivated exceptional attention to detail and creative problem-solving when standard approaches proved inadequate. This approach had transformed equipment maintenance from routine duty into professional craftsmanship that generated pride and satisfaction among crew members who took personal ownership of their mount's performance. Martinez and his fellow crew members competed to achieve superior mechanical precision, taking satisfaction in equipment reliability that exceeded manufacturer specifications through their dedicated maintenance efforts. The results demonstrated the potential that could be achieved when individual expertise combined with mechanical excellence. Mount Charlie 4 had achieved availability rates exceeding 98% during 6 months of intensive combat operations, firing over 15,000 rounds without experiencing significant mechanical failures. The crew's maintenance expertise had prevented problems that plagued other installations, while improving performance through modifications that optimized system operation for specific combat conditions. Combat effectiveness statistics validated this approach to technical training and equipment maintenance. Sullivan's gun crews had achieved hit rates that exceeded fleet averages by margins that indicated superior proficiency in both technical operation and tactical employment. Their success rates against kamikaze aircraft demonstrated the advantages that could be gained when human expertise enhanced mechanical capabilities rather than simply implementing prescribed procedures. The mathematical precision required for successful anti-aircraft operations demanded perfect coordination between multiple crew members performing specialized functions within compressed timeframes. Pointer operators needed to track targets with accuracy measured in fractions of degrees, while compensation for ship movement and target maneuvering. Ammunition handlers needed to maintain consistent feed rates despite physical demands that exhausted personnel during sustained engagements. Fire control personnel needed to calculate lead angles and range estimates that enabled successful target interception, while processing information from multiple sources including radar, visual observation, and communication from other gun mounts. The complexity required trained teamwork that could function effectively under combat stress that impaired individual performance and decision-making capabilities. Sullivan had developed training exercises that replicated combat conditions while building teamwork skills essential for effective crew coordination. These exercises emphasized communication procedures, backup responsibilities, and cross-training that enabled crew members to assume multiple roles when battle casualties or equipment failures disrupted normal operations. The result was crew flexibility that maintained mount effectiveness despite unexpected challenges that would have disabled less thoroughly prepared units. The broader implications of this training philosophy extended beyond individual gun crews to influence fleet-wide approaches to technical education and equipment operation. Sullivan's methods had been studied and adapted by other ships throughout the Pacific Fleet, improving overall anti-aircraft effectiveness through systematic application of principles that emphasized understanding over memorization and personal responsibility over procedural compliance. The technological superiority represented by Bofors anti-aircraft systems required human expertise for optimal implementation. But this expertise could be developed rapidly when training methods matched the complexity of equipment capabilities with appropriate educational approaches. The combination of advanced technology and competent personnel created defensive capabilities that fundamentally altered the tactical balance in Pacific naval warfare. American industrial capacity had provided the technological foundation through precision manufacturing and systematic quality control, but operational effectiveness required personnel who could maintain and operate these systems with proficiency that matched their mechanical precision. Sullivan and crews like his throughout the Pacific Fleet had proven that this human component could be developed through intelligent training methods that unlocked individual potential regardless of previous experience or educational background. The morning sun illuminated Mount Charlie 4 as Sullivan completed his inspection, revealing mechanical excellence maintained through human dedication that transformed advanced technology into operational capability. The precision engineering that made Bofors' effectiveness possible had been enhanced through crew expertise that exceeded design specifications through personal commitment to professional excellence. Japanese kamikaze aircraft approaching American naval formations would encounter not simply advanced weapons, but weapons operated by personnel whose technical competence and tactical proficiency had been developed through systematic application of training innovations that maximized human potential. The thunder of Bofors guns represented both technological achievement and human expertise, working in perfect coordination to create defensive capabilities that no attacking force could overcome through determination alone. The partnership between American engineering excellence and naval professionalism had created defensive systems that protected democratic values through mechanical precision, enhanced by individual dedication to collective security objectives that transcended personal safety considerations. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.